Hello, welcome to today's lesson on heats of reaction. Energy changes in chemical reactions. As we learned previously, many chemical reactions have energy changes. Sometimes these chemical reactions lose energy into their surroundings and therefore feel hot. These reactions are called exothermic. Sometimes these reactions absorb heat from the surrounding and they feel cold. These reactions are called endothermic. It is possible to calculate how much is given off or absorbed during a chemical reaction by using Hess's law. The formula for Hess's law is delta H equals the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. This formula looks a little complicated, but its practice is very simple. Scientists have been calculating how much heat is released or absorbed when a large variety of compounds form from their basic elements. These are available to us on a table of standard enthalpies of formation. Therefore, we can calculate the energy given off or absorbed by the reaction by adding up the heats of formation of the products and adding up all the heats of formation of reactants, and then taking the total products and subtracting them from total reactants. Please note, the values on the table are sometimes given in kilojoules per mole. Therefore, you need to multiply by the number of moles of substance in a reaction. Therefore, we need to make sure our reactions are balanced. So let's do an example. So how much heat is given off by the following reaction? 2HNO3 plus CaOH2 gives us CaNO32 plus 2H2O liquid. The state, if it's a solid, liquid, or gas, is important, and you will have to look at your table of enthalpies to make sure that you're getting the right value. So let's set up this equation. We know, I'm just going to zoom in here a little bit if I can. So, our delta H equals the sum. The symbol means sum, so you're adding up all the numbers that come after it. The sum of the delta H of the products minus the sum of the delta H of the reactants. So the delta H for the CaNO3 from the table is negative 938.2. We're going to add that to the delta H of H2O, or the heat of formation of H2O as a liquid, and there's two of those. So we have to multiply that by 2, and that is a negative 285.8. Now we're going to subtract the delta H of the HNO3. There's two of those, and that heat of formation is 173.2. We're going to add the heat of formation of the CaOH2, which is 985.2. Okay, and when I type all that into my calculator, it adds up to be negative 871 kilojoules altogether. So one quick note, elements cannot be formed, they naturally exist. Therefore, the heat of formation for any element in its standard state is always 0. These are not always listed on a table since you're expected to know that. All right, here's an example of a reaction where we have an element in its standard form. That oxygen there, we're not going to have to worry about. Okay, we just need to worry about the other 3 compounds. So again, our formula. So our delta H equals the sum of our delta H of the product minus the sum of the delta H of the reactants. So I pull out my table and I find all the numbers. So I have 3 CO2s. So that means I need to multiply the heat of formation by 3. The heat of formation of CO2 is 393.5. I'm going to add that to the heat of formation of the gaseous water. So you have to make sure that you're looking for the correct number. There's 4 of those, so I have to multiply the heat of formation by 4. So 4 times negative 241.8. Then I will subtract the heat of formation of the propane, the C3H8, which is negative 103.8. Okay, so I do all the math, I type all that into my calculator, and I end up getting negative 2,043.9 kilojoules. So that's how many kilojoules you will get if you react 1 mole of propane. So like I said before, that's how much energy you'll get if you burn 1 mole of propane, since that reaction only has 1 mole of propane in it. So how much energy would be released if we reacted 2.5 moles of propane? So that's very simple to do actually. All we need to do is multiply that number of moles so that changes our delta H. We're going to multiply the negative 2,043.9 kilojoules per mole. We're going to multiply that by 2.5 moles. Okay, our moles cancel out, which is exactly what we need them to do. and we end up with negative 5,109.75 kilojoules. All right, so our last example, you have a lamp that has 50 grams of kerosene, C12H26. How much energy can you release from completely burning this fuel? Delta HF for kerosene is negative 24.15 kilojoules per mole. So very similar question to the last two questions that we did, except for this one we needed to figure out exactly how many moles of kerosene we have so that we can figure out the energy. So I'm going to zoom right in just so I have enough room. So, as always, delta H equals the sum of the delta H of our products minus the sum of the delta H of our reactants. Okay, we've already looked at the delta H of formation of CO2 and H2O, so we can just look back to our previous question, but this time we have 12 moles of CO2 in this reaction. And we have 12 moles of gaseous water. The question tells us the delta H formation of the kerosene is 24.15 joules or kilojoules per mole. And the oxygen is an element in its natural state, so I don't need to worry about that. So I throw all that into my calculator, and I end up getting negative 7,599.45 kilojoules per mole. Okay, now I need to figure out how many moles of kerosene I have. If we remember back to our stoichiometry and our molar mass unit, to figure out molar mass, we multiply grams by 1 mole over molar mass. So I need to figure out my molar mass of kerosene, which is C12H26. So we have C's, and we have H's. So 12, the molar mass of carbon is 12.01 grams per mole. The molar mass of hydrogen, for the 26 of them, remember these numbers come from your periodic table, 1.00. When I do all that math, multiplying and adding, I get 156.12 grams per mole. And then I need to figure out my moles, so I'm going to take my 50 grams and I multiply that by 1 mole for every 156.12 grams, and I get 0.32 moles. Okay, we know that this number we found here is the number of moles, or the number of kilojoules per mole. We only have this many moles, so that means I need to multiply those two numbers together to determine how many kilojoules of heat are being released by that kerosene. So I will take this number, so my delta H then equals negative 7,599.45 kilojoules per mole. And multiply that by 0.32 moles. My moles cancel out, so I'm left with kilojoules, which is perfect. And I end up with negative 2,431.8 kilojoules. So that's the end of our lesson for today. We will see you in class tomorrow.